Good afternoon. So due to some technical problems, so today class got delayed by 15 minutes. So today we will mainly discuss the last class of this module. So that is on surface characterization. So mainly I'll focus three techniques here. That is, one is X-ray photoelectron spectroscopy, electron spectroscopy, and secondary and mass spectroscopy. So these are the three techniques that mostly used for mainly for surface characterization, that it gives information on the top surface or within the 10 nanometer from the top to penetration depth of 10 nanometers. In that top layer, we'll get the information using these techniques. So coming into surface characterization, that is quite essential because surface study of mainly it involves the outermost layer of the material that is less than 100 angstrom. To see, this is the 3D structure, and then on the surface atom that mostly that lies on the top surface here, and these surface atoms are of the order of its thickness is less than 100 angstroms. So here we can use two types of technique: one electron spectroscopy or ion spectroscopy. If you come into electron spectroscopy, so you use X-ray photoelectron spectroscopy. That there, another one is Auger electron spectroscopy or electron energy loss spectroscopy. So these are the three techniques mostly that electron spectroscopy involves. So on the top surface, this is the top surface. So there we are going to study, and then we have a near surface, and then bulk. So we mainly deals with these three techniques. We'll deal with on the top surface. So if that in X-ray photoelectron spectroscopy, where exciting the material, that beam that falling on the material is mainly that X-ray is in, and you will get electron out. But in case of Auger electron spectroscopy, we have electron that mainly you are putting onto the surface. Is the material and electron is out. You can also do the Auger electron spectroscopy using X-ray. That in XPS also you can do Auger electron spectroscopy using X-ray. Then a third one is I discussed this in case of TEM, that is electron energy loss spectroscopy, where is electron in and electron out. That gives your U oxidation state, coordination number, that illness and thickness. That's two techniques. And this XPS and this Auger electron spectroscopy, both of them will tell you the information about the surface characteristic, and that will you will get that oxidation state of the materials. So the other one is ion spectroscopy. So there we have secondary ion mass spectroscopy, that is the SIMS, as well as sputtered neutron mass spectroscopy or ion scattering spectroscopy. In all these three, this ion spectroscopy, you are bombarding the material with ions, and you're again getting ion out, except that in the sputtered neutron mass spectroscopy, where you will get a neutral particle out. So I will mainly focus on X-ray photoelectron spectroscopy, Auger electron spectroscopy, and secondary ion mass spectroscopy. Now coming into X-ray photoelectron spectroscopy, so XPS, that is a technique based on, it's about the Einstein's photoelectric effect, which was developed by 1905 by Einstein. So that photoelectric effect, as I told that if you have a material, you apply some photon energy, that X-ray or H nu energy you apply, and then you have if that overcome the binding energy of the material, then what will happen? If that H nu that is greater than the binding energy, then that electron will knock out from the core material. So that electron is called photoelectron. So that photoelectron, that's the main basis of this X-ray photoelectron spectroscopy. And then because of this photoelectron effect, that Einstein got Nobel Prize in 19. This is not, it's 1921, it's mistaken, 1021 it's written. So during the mid of 1960, Dr. Saiwer, Siguen and his research group developed XPS techniques. So XPS was later on developed in 1960, though the principle was developed much before. So if you see the basis of the X-ray whatever information you will get. That XPS is also known as electron spectroscopy for chemical analysis. If you see the term, for chemical analysis, that means that is mainly useful to get information about the elemental composition and its oxidation state. It's widely used technique to investigate the chemical composition of the surface and used for determination of chemical composition, chemical state, electronic configuration of the material. You can see here, if it is a material on the blue one here, that is the top surface, and that one we are mainly 1 to 12 nanometer. Within that zone we are mainly exploring. So here in this is the area of interaction, that is the volume of interaction. So 1 to 12 nanometer at the top surface, that only we are looking. We have a X-ray beam falling on the material, and penetration depth of X-ray is about 1 micron. But we are only dealing with 1 to 12 nanometer on the top layer. So electrons are extracted only from the narrow solid angle that will be used for X-ray photoelectron spectroscopies. And here, an electron moving in a solid, if you go for an XPS study, that electron moving in a solid can interact with the electron of different layer and lose part of its energy. Like once that you excite with X-ray photons, so now electron will come out. So that electron move in the solid and interact with the electrons of different layers. Like in a material, you have a different layers are there. So you have a core electron here, and then you may also find other electron on the top surface, on the other valency band. This is the core. So the core electron is coming out because of the bombardment of light, that photon, X-ray photon. So this electron, while coming out, that can interact with neighboring electron, that other electron. It can lose part of energy by inelastic process. So average distance traveled by the electron before an inelastic collision is known as inelastic mean free path. Like it started from here, and before it's going out, it should come out this outer space. But before coming out, so it will interact with many electrons inside. So the average distance that electron travel, like another electron is here, that these to this distance. So before that electron, before interacting with the another, for facing a collision, so that distance is called inelastic mean free path distance. Since the energy used in XPS order of 50 to 1200 electron volt, the lambda is here very, very small. Okay. So photoelectrons, the originating from the atomic layer very close to the surface. That's why XPS is a surface specific technique. So though we are removing the core electron, but that photoelectron is generating is mostly from the top atomic layer. So that's why it's a surface technique. And XPS peaks resulted from electron reaching surface without any inelastic interaction. And the probability that emitted electron reaches out the surface as a function of depth equal to P, the probability of that particular electron coming out of the surface e to the power minus d by lambda. D is here the depth. So if you see here, this is 1 lambda, this is here is 63%, this is 2 lambda, this is 3 lambda. So the probability of coming out of electron is generally in the order of here is 99% probability is order of 3 lambda. So there the electron is coming out. You can see here is the 95% that you are getting of the order of 3 lambda. So 95% of the measured electron originate from the depth is a region of 3 lambda. So that means that the electron that are originating from here in this area 3 lambda zone. So here, so this is that is the main from the 3 lambda depth. So if you see that intensity I0 is falling here and IS is from the sample is coming out, that IS equal to I0 d to the power minus d by lambda. Since here we have a 3 lambda, if you integrate over 0 to 3 lambda, so e to the power minus x by lambda dx by e to the power infinity if you will take, then you will get 0.95. That's why that number that XPS is based on a photoelectron process, and the maximum that 95% of the measured electron originating from the depth of 3 lambda. So here, if you see the principle of photoelectric process that happens during X-ray photoelectron studies, so here that you have a conduction and valency band. Inside valency band, you can see 1s, K, L, 2p, all those are in the core electron. Here is 1s electron. So once you apply that H nu, that H nu, that is the X-ray photon, you are applying here X-ray photon. So because of this, first will have what will happen, that atom or molecule or the system will get ionized, and you will eject an electron, A plus an electron. So electron is emitted from the surface when a certain kinetic energy by the absorption of X-ray photon. So the X-ray photon that you are putting on this, so that X-ray photon will fall on this, and then because of this, if you can see here, when the X-ray photon is coming here, falling, and then that's what is happening. This core electron is coming out, and that electron will come out with a specific kinetic energy. That means your kinetic energy of that electron which coming out from the core level, which is H nu, that is photon energy minus binding energy minus work function of the material phi. So that is that means that H nu has higher than overcome the binding energy of the particular electron inside that layer, then this electron will jump, it will take out and it will jump here. So the vacancy will be created inside that. The photoelectron energy here, that is depends on the photon energy. So whatever the electron will be, this electron will bear, so that energy will depend upon the how much that photon energy you are exciting. So that if this equation satisfied, then only you will inject a photoelectron, will have some kinetic energy and it will come out. And then here you can see there are many electrons. There is your 1s electron, 2s electron, 2p electron. But we are mainly interested about this core electron of 1s. Why so? But because if you see an electron near the Fermi level is far from the nucleus. If you see here it is a valency band, it's conduction band, and your Fermi level here lies, that is in between that conduction and valency band at this place. So the electron which lies near the Fermi level is far from the nucleus. Nucleus is much in inner side here, and that this electron is very far away from here. So moving different direction all over the place, and will not say, so this valence electron, that electron is the near Fermi surface, that first of all are far away from the nucleus, and they're randomly moving in every different direction all over the place, and will not carry much information about the material, about the atoms. So that means Fermi level, the highest energy level occupied by an electron, neutral, solid, and 0K. This is here. So that means the electron near to the Fermi level doesn't bear much information. So the core electrons are located close to the nucleus. The core electron here, so they are located close to the nucleus and have binding energy characteristic of that particular element. So because of that, it will give you that elemental composition, information about the environment of the atom. You can see this is valence electron is quite far away, that is core electron that is close to the nucleus. And being close to the nucleus, it will give much more information than that of the valence electron. So you need every material or every atom that has a particular binding energy that that electron is bound to the nucleus. So this binding energy characteristic of the core electron is for each element is different. So determined by the attraction of the electron to the nucleus, how the electron is attracted to the nucleus. So that is binding energy. So you can see this nucleus, this is the electron. So here this point with zero energy attraction between the electron and the nucleus here. So beyond this point, the atom is free. You can see it here. It's like electron is free from the atom. So only that the core electron, they are attracted towards the nucleus, and they have a particular binding energy information. And eventually there will be a point when the electron will be free from the nucleus. This is the point. So if you see the initial state is BAB, so then what will happen? One additional charge you will get, so A plus will go to oxidize that initial state. If 2 electrons is here, you can say 1 electron is coming out. So binding energy here is the final state, this minus energy of the initial state. So that is the binding energy. So that binding energy is, electron is bound to the nucleus by that. The photon energy has to overcome that, then only that process will it occurs photoelectron process. As I told, in addition to photoelectron, there is possibility of Auger electron, formation can be occurred. So you can see here, if you see, when a core electron leaves, this core electron is here. So this core electron leaves here. So what will happen? A vacancy will be created. And this vacancy can be filled by an electron at high energy level. You can see here, this is the electron at high energy. So this electron now comes down here. Now a vacant space is created here. Since this electron which coming from higher orbital to this here, so that has high energy. So because of that, because of the excess energy, so another electron can be knocked out from this. So that you can see that this emitted electron is a Auger electron process. This is a 3-electron process. This 1 electron involved from here, then second electron, then third electron. So it's a 3-electron process. It's a radiation-less internal rearrangement. And here, this is one possibility that the Auger electron is generated. In addition, some X-ray fluorescence can also be possible. So depending upon that which orbital it involves K cell. Initially, the K electron is going out. If you see that, if you see here, initially the K electron was not here. The first involvement is K cell. Then L cell electron is coming out. Then another L cell electron is going out. So it's involvement of K, L, L. So it's called KLL or J electrons. So depending upon that, you will have different Auger electron can be produced. So kinetic energy of the Auger electron will be the kinetic EK, kinetic energy of the photoelectron minus L2, which falling here L2 and L3. So minus work function, energy of L2 atom, L3 atom, and minus of 1. So Auger electron does not depend on the photon energy. Whatever the photon energy you apply to remove this core electron out, so there photoelectric effect was depending upon this, but Auger electron was not depending upon this incident photons here. So that instead depends upon this how much the energy all these two EL2 or EL3 is there. So if you see the Auger electron process, I told it's a 3-electron process. You can see the X-ray in case of XPS for Auger electron spectroscopy, and electron in case of AES spectroscopy. Auger spectroscopy, you can see one X-ray or electron is coming here. So because of that, this electron is coming out as a free electron, and vacancy space 1 is now created. To fulfill this, the electron 2, the electron of higher energy, that will occupy from here to here, to jump to here, and that will occupy this vacancy space of 1. So now another vacancy place is created at 2. So but this electron being at high energy, so because of that, the excess energy is released, and that electron will be that will have sufficient to knock out this electron, and this electron will come out. So this is a 1, 2, 3 electron process, and you can see the kinetic energy equal EK minus L2 minus L3 minus 5. So mostly photoelectron process is a directly involvement of one electron that's coming out, but in this Auger electron that's involved in 3 electron process. If you see the probability of simultaneously both Auger and X-ray photoelectron can be possible. So if you see the probability which one will dominate at what atomic number, if you see, you can see here at lower atomic number, when atomic number is lower, there you see the X-ray photoemission is less, and it increases with increasing the atomic number. When you have a high Z material, that will follow the X-ray photoelectron emission will be higher. But if you go on the opposite, Auger electron follows the opposite path, that is low atomic number. You see the Auger electron is probability is high, then it decreases when it goes down to increase to the atomic number. Yeah. So the X-ray, that agar yield will be 1 minus XX, that's related to the fluorescence X-ray. If you subtract that one, you will get how much Auger transition which takes place here. So if you see the instrumental part of the X-ray photoelectron spectroscopy, so this is a typical photograph of X-ray photoelectron spectroscopy. On the trough surface, you have a source here. That source is nothing but you can use a dual anode source. That means it has a monochromatic aluminum or magnesium. Here you can see the electron, that the energy is about 1486 electron volt. and magnesium is about 1553.6 electron volt. So that the energy is huge in case of XPS analysis. And X-ray flux at the high X-ray flux at the sample. So if a sample will be aligned somewhere here in the chamber, so they are the flexure flux of the sample. And it has a narrow X-ray line width. With these two, aluminum and magnesium has narrow X-ray line width. As you know, that this X-ray photoelectron spectroscopy is mainly an absorption technique, that X-ray photon is coming or falling on the sample surface, so that will be observed at the same time it knock out a photoelectrons. And if you see here, the magnesium and aluminum is mainly used as a source in case of XPS analysis, whereas copper, or chromium, they are used in XRT source in X-ray diffraction studies. If you see, but this copper will not be used in case of XPS, but magnesium and aluminum is used. The first thing, the reason behind this is X-ray photoelectron spectroscopy is an absorption technique. So this is a scattering technique, that diffraction technique in case of XRD, where you know the energy should be quite high. So that will be diffracted from the top and on the surface. But in case of here, XPS, first of all, it's an absorption technique, and then this you can see here the magnesium, magnesium or aluminum, the width, that very width, narrow line width 0.7 to 0.85. But you see copper, your bandwidth narrow is quite high, 2.6. So because of the narrow line width, and you have appropriate energy suitable for surface information, so that's why you'll be able to use this magnesium and aluminum as a source in XPS studies. Like you have both magnesium and dual anode system here, aluminum, both are there, so both can be used as a source material. And then for XPS analysis, you need ultra high vacuum. That means pressure is the order of 10 to the power minus 19 turn, that is used. If you go for the SCM, it can be about 10 to the power minus 4 to minus 5 order. In TM, it is 10 to the power minus 6, minus 7 order. But in case of XPS, it's order of 10 to the power minus 8 to minus 8. Because it's high ultra vacuum, that will be remove the surface contamination and absorb. Like if a surface is contaminated, that will interfere in the XPS analysis. So in high vacuum, what will happen? This remove the surface absorb contaminants, so the order of ultra high vacuum, so that will be used. So enable emitted photoelectron to be analyzed without interference from the gas phase collision. Like if you take a gas phase inside, if there is no vacuum, so it can that photoelectron can interact with the air inside or in the gas argon or something that may be inside. But if you do the experiment in ultra high vacuum, so that the interaction of the photoelectron, but there will be no interference from the gas or collisions. So it will increase the mean free path of the electron, photons or ions, and prevent arcing and voltage breakdown. So you have to take a high vacuum, because what will happen? So at high vacuum, that it remove the contamination and it will increase the mean free path. And here another system that we need is the ion gun. So that ion gun is nothing but this argon or bombardment, so that you want to see layer. This is the layer structure. You can see this top surface first you see, then you reach out with argon bombardment. Now go for analysis the second layer, then third layer, then fourth layer. Like this, you can able to analyze layer structure by using depth profiling by using such argon gun. It will, because of the argon air plus bombardment, top surface will leach out, and now it's exposed to the inner surface. So depth profiling is possible in case of this. And here that it has that mostly electron analyzer that is there. So that electron analyzer is a hemispherical analyzer that is used to collect lens system to collect the photoelectrons. So disperse the emitted electron according to it collects the electron, then they separate out based on their kinetic energy, thereby measuring the flux emitted by electron of particular energy. And two types of electron analyzer used. One is a hemispherical electron, HS is a hemispherical one, and then another was a cylindrical mirror analyzer. If you go to the hemispherical analyzer, what will happen here? the positive charge of inner surface here, the positive charge of the inner plate to attract the electrons, and outer surface that is negatively charged to repel the electron, to move the electron in the orbit. The electron is producing from the sample here, then it's going to the detector. So before going to here detector, so it go through this analyzer, heavy analyzer, that inside that potential is is inner plate is a positive potential and outer plate negative potential. If anything come out, it will again return back to the core inside. So that's why here it is positive negative potential is provided. Only electron with specific velocity, so that can reach to the through the analysis to the analysis plate, because so we need a particular velocity to collect that electrons. So, but in case of cylindrical analyzer, CMA has two concentric cylinders at different voltage. And you can see the X-ray source coming on the sample. Then you can see one concentric here, and here is another. So there is a two. If it is one, this is two concentric. The one of the material cylinder kept at a positive potential, while other one at 0 voltage to create an electric field between to the cylinder. You can see here, this is 0 potential here, and this is 1 positive potential. So what will happen? The knockout electron move between these two, and then slowly these two will come to the detector. When charge of the cylinder voltage, the acceptable kinetic energy will change, and that determines the electron have kinetic energy. That is kinetic energy equal to h nu minus binding energy minus work function. So electron detector system measure mainly the kinetic energy of the electron that coming out from the core. It will measure its kinetic energy, and based on that kinetic energy, h nu you have applied, and kinetic energy that you have that you obtained, and work function is for each estimate. So binding energy can be calculated, and this kinetic energy will give you specific characteristic of the electron. If you see here, you have a conduction band and a valency band, and then a work function. So here that the core electron will jump out, and you will get this equation here: kinetic energy equal to h nu, it's binding energy minus phi. So binding energy equal to h nu minus starting energy is minus phi. So the photoelectrons peak reflect this create binding energy of the electron present in the solid. Like if you take a solid, and on that solid now you bombarded a photoelectron. So whatever the h nu you bombarded, so whatever the photoelectron is coming out, and that photoelectron will be mainly corresponding to a particular element. You can see here, this is a manganese of zinc oxide. You can see the signal from ZNO and ZNO oxygen and magnesium. So carbon 1s peak is mostly we used to observe in X-phase analysis. That is because of advantageous nature of carbon in atmospheric carbon monoxide, carbon dioxide, that sometimes detects inside the detecting the material. So if you see the electron interaction, and if you see the XPS spectra here, you can see. So here it's going like this, then there is a jump, then like this, then there is a jump. So this background is not, instead of going a straight background, it's going like this type of step function background. So that's because of mainly noise level, that noise signal comes from the electron that collide. That electron coming out from the core electron, before reaching on the surface, it will collide with the other electron. You can see that X-ray falls, and this electron will now come out. So once it come out, it can follow this path, it can follow this path, it can follow this path. But whenever it's coming out, that electron will interact with the other nearby neighboring electrons. So there will be an elastic interaction. So collision causes a decrease in energy of the electron. So the energy, that electron that coming out from here, the higher energy. So once it goes colliding inside with the other material, other electron, what will happen? You will be able to see, that because of this, the elastic collision takes place. So background noise is the increase with the binding energy, and the sum of all noise is taken from the beginning of the analysis. You can see your N1 here, then some binding energy gain, then some gain, then some gain. So N total, that noise is equal to noise involved in this state, in this state, in this state, in this state. So that's because of the collision that those who are coming without collision, that is different thing. Those coming with collision, that will energy some loss because of this interaction. If you see the XPS, if you see that they have a particular peak notation, like you do 1S peak, 1S peak, 2S peak, 2P, like that, whether it's 1S1, 1S2, 2P, 3 by 2, 2P, 1 by 2, or D5 by 2, D7 by 2. All those things will depend upon LS coupling, their RS coupling, you can say. So J equal to L plus or minus L. L equal to 0, then is single peak XPS. L is greater than 0, that means a doublet will observe. So if you see here, the S is equal to plus half, 2 electron, another electron S is equal to J equal to Y plus S equal to plus half, and S equal to minus half, down 1, and up 1 is plus half. So J equal to L plus or minus N, L plus half, L1 minus half. So then there is a two thing is possible here. But if you see for this P, for PDF, two peaks are observed. You can see here 2P 3 by 2. So J equal to 1 plus 1 by 2, J equal to 1 minus 2. So then is 1 by 2 here from, if it is added, is different, then is subtracted. You will get depending upon, depending upon the 2P, whether 3 by 2 or 1 by 2, L equal to 0, as you know, quantum number, L equal to 0, S orbital equal to 1, P orbital to the 2 orbital, F equal to F for F, which is 3 orbital. So I plus 1 by 2, the P, if you take in, that's 1 plus 1 by 2, you have a 3 by 2, and 1 minus half equal to 1 by 2. So this 2P 3 by 2 and 2P 1 by 2 is possible. Similarly, you can see the D orbital, or F orbital is I equal to 3. So SOS, and the higher, if you see that here 2P and that means higher order. So spin orbital splitting, you can see Zn here 2P 1 by 2, 2 by 3 by 2 at a distance of 23.1 electron volt. So that is mainly the SOS interaction that you will be able to see. So required to identify the peak position, peak intensity, and spin orbital coupling of the element that you will be able to get information. So what are the chemical information from the core level that we can obtain from the expression analysis? Mainly, it provides binding energy, it gives binding energy that provides the chemical environment of a material. Upon bond formation, you see this is the valency band, it's a core electron, is tightly conjugated with this. Here, if you upon bond vibration, if you take bond, apply some energy, bond vibration, the valency band electron density changes. So whatever the valency band resulting in adjacent of electrostatic potential affecting the core electron. As the valence electron density will increase in case of bond formation. The change in bond and binding energy of the core electron cause the shift of the corresponding photoelectron. So once the binding energy of the core electron is changed, so accordingly that kinetic energy that cause shift in the corresponding photoelectron, that is called chemical shift. When atom loses valence charge, that is Si0 to Si plus 4, that means that 4 electron is gained here, so binding energy is increasing. So here atom gains valence charge, that gains valence charge, so oxygen will O2 minus, the binding energy decreases. You can see here how this express analysis is able to distinguish different oxidation state. This is silicon substrate, and then they're depositing silica. You can see silica in +6, +2, +1, +4. It exists in different oxidation state. So those oxidation state can be identified by express analysis. Then you can see here, this is another example of silicon fluoride. So silicon metal, 0 oxidation state. Then SiF1, 1 oxidation state, 2 oxidation, 3 and 4 oxidation states. All these oxidation state we're able to find out difference by using X-ray photoelectron spectroscopy. So this is an example of that core level X-ray spectra. If you see here, this is a Fe3O4 magnetic nanoparticle. You can able to see nitrogen, which is a nitrogen coated. There's glutamic acid here, butyric acid. There is amino acid that have nitrogen. So nitrogen on S, carbon, and oxygen on S. So this oxygen is mainly present as a Auger electrons. Like that this corresponds to not a that XPS oxygen 1s line. So carbon you can see here, that is carbon from the coating or from the atmospheric carbon dioxide. So before going for XPS analysis, what we have to do? So first we have to take care of the chemical shift of the instrument. Like for example, if your peak of the carbon, so generally carbon and gold, that two things you take as a standard in case of XPS analysis. So we used to either gold plated your sample, gold coated, or you can simply using carbon coating or using carbon as a standard. What will happen? So that carbon peak has to always appear at 285 electron volt, or some people use 284.6 electron volt. Either one you can take. So this is the position of the carbon 1s peak. If the instrument has some shifting effect, so this peak may be shifted to here or shifted to here. If it is shifted to here, then you have to subtract that. What is the distance when there is shifted to here? You have to subtract what is the distance from here to here. So depending upon the this how shifting that is takes place, instead of this, it is shifted to. So if it should be appear instead of here, if it is appearing somewhere here, then what will happen? You have to subtract that much. How much shifting is here? It is here. Then you have to add that much electron volt. So carbon either at 285 or 284.6, you have to fix it, and by taking care of chemical shift, then you analyze. So you can see here this is Fe3O4 nanoparticle coated with amino acid. This is nitrogen signal is highly symmetric. This is iron signal. This is oxygen and carbon signal. You can see here the carbon that is fitted into 3 lines. So you can carbon, that hydrogen, that stoichiometric, that carbon in the material, the coating agent or atmospheric carbon, that will be at here 285.0, and then carbon, oxygen is high electronegativity, and the nitrogen, then nitrogen, then oxygen, nitrogen both here. So because of that, what we'll see, the depending the chemical shift, the peak position can be identified at 285 is carbon, then here carbon and the oxygen is there. So depending on the electronegativity, it will pull down. So you'll see here, and it will see all these positions. Similar oxygen also you can deconvolute using the XPS. One technique, one is XPS peak fit 4.1 or XPS peak fit 4 or cassava. That is the two. There are many other software is available, so you can use those software. So you can identify that. You can see oxygen iron is +2 and +3 oxidation state. Here is a Fe3/2, Fe1/2. Then this splitting constant SOS is fixed for a particular material. So similarly, some other example, if you see, so you can see here, as I told that carbon oxygen bond, that simply if you take carbon and you have oxygen, if you see that oxygen atoms, that electron oxygen atom attraction, that is oxygen is high electronegativity and that of less electronegativity of the carbon. So because of high electronegativity, what will happen? The electron cloud will be stretched up towards oxygen. So because of this, the binding energy in case of this will be shifted. When you have a carbon here at 280.5, the carbon oxygen is shifted to the higher binding energy, and that is because of this that is depend upon the charge in local environment of the carbon due to the oxygen interaction. Whatever the charge on the carbon, that will decide how the bond will be shifted the particular direction. You can see here carbon peak and carbon nitrogen, the 2 oxygen is there. So this will be more stretched. So depending upon that, you can find out how the electronegativity will affect the this chemical shift. So you can see another example by XPS study, the inorganic material, that is zinc, the manganese doped zinc oxide. This is a manganese doped zinc oxide material on which co-doped antimony, bismuth, steel, they were co-doped. Here you can see, so there is when the Zn is pure Zn, two peaks are available to here, 2p1 by 2, 2p3 by 2, they are about 19.1 or 2 electron volt distance. But when you go to see clean and bismuth, can see that peak is get broadened and stretched to a higher energy side. But in case to bismuth, you see there is a completely split into this 2p1 by 2 and 2p3 by 2. So that how the manganese oxygen and how that manganese doping affecting the or co-doping material affecting the metal properties that you can see here. So you can see zinc has 1.35, manganese 1.55, but SA and SB bismuth, they have quite high electronegativity. So because of that you will get Zn and peak that will be broadened and shift to the higher electronegativity. So bigger the electronegativity of the binding and about larger the binding energy of the electron that you observe here. So in addition to the X-ray photoelectron peaks, so you'll be able to see satellite or Chekhov peaks. That satellite peaks is mainly, either it can be Chekhov or Chekhov are due to a sudden change in Coulombing potential as photoelectron passes through the valency band. Like here is the valency band, this is the valency band, and this is the conduction band. So that the electron is coming out from here, here electron is coming out, and due to the sudden change in potential, the photoelectron through the valency band, when it reaches to the valency band here, so there may be a sudden change in valency band due to the sudden change in Coulombing potential when passing through the valency bands. So it will interact with that probability. So you have a that sudden change in you will be able to see. So that change will maybe either shake up or shake up or shake off. If you go to shake up, the outgoing electron interact with the valence electron. So you have valence electron here. So whatever the electron coming out, so that will interact to the outgoing. The outgoing electron interacts with the valence electron and excites it to a higher energy level. That's called shake off. You can see this is the shake off. 1s2s2p deconverted like 2s2p, 2p and 3p. So there is a probability of shake off and shake off. This is the main peak here. If the valence electron ejected from the ion completely, the continuum in case of shake off. So it appears as a broadening of the core level and shake off satellite broad peak feature at lower energy with respect to the main line. So you can see here it's a highly noise system that your background noise is quite high. So that is because that shake up and these two interfere. So you can also do depth profiling, as I told at the beginning, by using XPS analysis. You can see here we have a cured XPS substrate here, and sample here, then you argon each out, remove the atom, now you are inside. So now you measure here inside morphology here. So that means you have if a silicon atom, you can see an example of silicon and silver, silicon 2p, you can see how the intensity of the silicon is increasing in this, whereas in Ag also you can see that. So you will get the peak intensity increase because you are going inside that depth profiling. So you can find out that in the different layer structure, how the different atoms are distributed. See this is mainly in depth profile analysis, mainly a destructive profile. You can see your silica SiO2 Si substrate here, then L2O3, hafnium, L2O3 and platinum substrate. You can see this example here in TM image, SiO2 layer, titanium nitride, HFO2, L2O3 top layer and glue. So if you see the XPS analysis, you can see how that oxygen is varying. If you see the oxygen 1s spectra, first of all, that one you can see the red line. When Al2O3, that's a line when you are going like this, for example, when you are at Al2O3 line, you started here and it comes to the Al2O3 line. Initially, on the top surface, you have platinum. So there is in the platinum zone, there is no peak. So then aluminum region is slightly increase and reach the maximum, and then it decrease to. But if you go to the Al2O3, that you can see that how the Al2O3 is varied here, that here inside, so initially it's high, the top surface, then it decreases. For example, this black one, that is mainly oxygen. I told how the oxygen, here you can see the top surface, the oxygen is there and going inside silicon. So there is no. So you can able to identify the distribution of the element in the whole system by using this XPS depth profile analysis. So in addition to depth of analysis, XPS can also use a non-destructive way, that is AR XPS, non-destructive XPS. You can use angle result XPS analysis. You can see here that this analyzer is here in the top, this here in the from the bottom, from the vertical position at the top, and then its normal position, then X-ray beam is falling here. So you can see here that penetration depth, if you see the analysis, the material is this width only. This is the surface you will able to analyzing in here on the surface. But if you go to tilted the material with an angle result at 10 degree, that detector is kept at 10 degree, here is a 90 degree less surface sensitive. You can see here the detector is collecting data in such a long. So instead of a short range, here is a long range collection. So that means non-destructive depth profiling is possible by varying the electron takeoff angle, by varying this, how the electron is coming out. So if you consider that one, you can see the SiO2 Si substrate. Whenever you have a vertically, you take this 90 degree, you can see the binding energy of oxide you are getting here, but that of metal also you are getting. Well, it passes through here vertical, then it go inside. So oxide top layer you have peak in here. But if you want to see only surface information SiO2, you tilted it. So you, because instead of like straight, now it is like this. Interaction, so small interaction information will able to get using this. And this depth profiling analysis can also be used by non-destructive way. You can see an example of a solar OLED structure. You can see how the different So I was disconnected due to some technical, internet issue today. Internet is little down here. So now we are discussing that depth profile analysis by non-destructive way. You can see here one example that thiol is that long chain thiol molecule is getting deposited on the AU surface. So you can able to see how these thiol molecules are embedded, how they're distributed. You can see that, for example, if you see the sulfur, you can see some sulfur is there here. So first two layer there is no sulfur. You can see here up to this much depth there is no sulfur, and then you are able to see the sulfur peak. One is go here, and then it goes down. So for example, gold is on the bottom one. You can see there is zero gold here. Once it reach the bottom layer, you are able to see the gold. Or is it this CH2 carbon chain are in between. Here you can see the in between center of the carbon chain. Similarly, oxidation state on silicon nitride surface, if you reinforce how the silicon and nitride formation at different angle is 90 degree. If you see here, your peak is, mainly it going inside, that you are able to see the nitride peak here. That you have a silicon SiN3 on oxide on silicon nitride, that means on the top surface oxide that is producing here. So you can see here that nitride peaks are here and silicon is there, but you will not be able to, you can, by increasing the depth, so while you can able to see that peak corresponding to, silica, the different with oxidation state, that, SI peaks that you can observe depending upon the, layered structures. So you can also get quantitative information using XPS analysis here. That here, if you simply by seeing the peak is like this, or you can calculate the peak area, that is area under the peak. So if you, that you find out, then you have a intensity, that if two samples are there, that one is IA is the peak of element, peak area of element A. For example, you A and B element are there in a material, and if A peak area under, if you get a two peak like this type of two peak in XPS, peak A and this is peak B, and B area under A and area under B is IA and IB. Then you have a sensitivity factor that SA is specific to each instrument or corresponding element. You can see carbon, your sensitivity factor is 0.29, silicon sensitivity 0.17. So that is the sensitivity factor. If you know, then you simply can calculate that the atomic percentage intensity IA area of the PK by intensity, that's sensitivity factor of that element to the particular instrument SA, and summation of these two, the AB. So this will be then IA by SA plus IB by SB. So that means in summation of IA by SI into 100, you'll be able to get the atomic percent. Sorry, this is the one example I have shown. This is, you can see the peak of having sample having carbon, oxygen, nitrogen, and sulfur, and you calculate the surface area, and you know the sensitivity factor by using the formula. If you want to calculate silicon percentage, you see ISI, that is the area of the peak, that here 2294 divided by sensitivity and divided by summation of silicon, carbon, oxygen, and nitrogen. You'll be able to get that, that sensitive quantitative percentage of the particular element. So you can also get, in addition to quantitative, nowadays imaging can also possible by using X-ray photoelectron spectroscopy, that you can see if is a photograph of a paint where in the bottom coat, your clear coat, and then you have a surface coat is there. You can see how these different layers are these. If you scan across different layer using X-ray imaging, you can take electron mapping, you can see carbon here on the top, and then you have oxygen here, and then you have a chlorine zone, then you have a silicon zone here. So you can able to, calculate different element. Again, carbon, only carbon, if you see how the different type of carbon is deposited on the material. If you have a carbon one, C1, CH, CHCl, double bond O, all these type of structure on the surface, you can able to find out. If this is the area, the mapping area is here, so you can able to find out where carbon is where silicon is where. So those info here is silicon mainly. So XPS imaging is possible by moving sample stage by so small X-ray spot size, or by using scanning plate. like ACM, here you can use a scanning plate, and then you collect that where the X-ray electrons are coming, and you can able to get this mapping structures. Okay. So far the X-ray photoelectron spectroscopy, as I discussed, is mainly deals with identification, the oxidation state of the material. You can able to get the information in a depth by depth profiling or by angle resolve. You can able to get thin film structures. Here you can get layer structure by those, and then also electron mapping is possible. So other technique that is OJ electron spectroscopy, that is also used for surface characterization. So here the principle is, as I have already discussed, a 3-electron process. So that here you have an electron gone on the target material here, then there electron will from the sample, the electron will knock out and it go like this and fall on the detector here. So here by optional ion electron source is mainly here. From the electron source, you are bombarding electron here, then X-rays will knock out, electron will knock out, and it will go to the electron detector data acquisition. And here you have an ion source that is for depth profile analysis. So you can able to do element analysis, you can chemical states or depth profiling, quantification, or scanning or spectroscopy that you can use, or the elemental mapping. So all things are possible similar to XPS. So they are first discovered 1923 by Meitner, but later independently again discovered by Perry-Agar. By her, the Perry-Agar, it was named as this. So Perry-Agar, by his name, the instrument was named as OJ electron spectroscopy. Which also, that is, as I told, it's a 3-electron process. You can see the first that the X-ray beam is being fall, and then because of this X-ray beam is falling here. So what is this electron? You can see it goes to ejected that core electron, primary high energy electron that will come and fall here, and it will go out. That electron go out, and you will have a hole here, and then this hole will be filled with another electron here. This electron migrate to here. Then because of this, you have open space created, vacant space created here, vacancy, and that empty orbital being the higher orbital, the energy is high, so that will probably knock out another electron. So this is a 3rd electron radiation-less process, the process of excited ion decaying into doubly charged here, because the 2 electron is doubly charged ion by ejection of an electron, which is called OJ electron process. As you know, that lithium solid, if you see lithium Li, that solid, if you take that, and if you take lithium isolated atom, that only lithium is the isolated atom and a lithium solid. So in atom, you have only 3 electrons, so it's not possible by detect by using this OJ electron spectroscopy. But in solid, you have different layer of lithium atoms. So there is possible to use this technique for surface characterization. I have already discussed this, the nomenclature of this line, OJ electron spectroscopy. You can see first the K electron is involved, the incident beam coming out, K electron is going out first. So K electron involved, then 2 K electron is creating vacant site here, then L1 electron, L1 is falling here, then because of that extra energy, L2 is going out. So that means K, L1, L2 is this line that can be named here. So symbol depending upon this, you can KLL, KLL, LMM, LLM. So all the LVB, all those possible can be done by nomenclature, can be done by involvement. But here, instead of X-ray photoelectron spectroscopy, here we used to get this type of intensity peaks here. But here, though we get that peak, so we have to go for a this derivative analysis, derivative of that intensity versus kinetic energy, dNE by dE. Then you see this type of spectra. So there you will be able to identify for this. Samples are irradiated by electron down. In AES measure kinetic energy of all electron with atom 1%. And for quantification and reduction the background noise, the derivative form of data is mainly used. To reduce the noise, you can see that it's the nitrogen here, copper here. So those type of derivative peak you can use to identify that particular element with kinetic energy. You can see this is the kinetic energy versus intensity, derivative of intensity T. So you can see boron, barium, boron, carbon, all those peaks at different binding energy, kinetic energy is possible. And if in transition metal, you can see here chromium, manganese. So you're able to also electron spectroscopy in different, you can see the differential distribution characteristics and element analysis by comparing with the standard spectrum. If you're getting a peak set here in the region of 5.781, you compare with that of literature data database, you'll be able to identify which was the peak, and relative intensity of Auger electron can be huge for the relative intensity, that can be huge for quantification. You can see here, this is the here instead of peak area, here it's mostly take commonly as peak to height ratio. So in the XPS, we are taking peak area, but here this is the peak that cover. So this is the height of the peak that we are taking. So peak to peak height if you take, and then you individual other peaks you consider and sensitivity factor, so that is you'll be able to find out the different constituent of the element. So here the depth profiling is also possible by using this Auger electron spectroscopy. You reach out the top layer and go inside, and further reach out and go inside, and you be able to get the depth profiling. If it is a layer structure, by using depth profile, you can see how the titanium is varying in different layer, nitrogen or oxygen, they are varying. The depth resolution depends upon it, how the ion beam, the bombardment you are doing ion etching, so depending on can go, that depend upon the ion beam energy and surface, how the sample surface is roughness and type of material. Soft material, you can go little more depth. If it's a hard material, you can go inside. You can see here silicon is bottom layer. You can see only silicon is see at the end when you reach at the such a length. This far of shorter time with, because first this layer goes out, this layer goes out, then you will reach a longer spotter time will take. After that spotter time, you can see this silicon is there, but immediately you can see that titanium, the top titanium, the cyan color titanium, immediately it comes and then sticks. So you can able to show the depth analysis, and you can combine the scanning Auger electron microscopy with like SEM image. You can see here is the SEM image of the particular material, and the same material you can color coded by using composite Auger image. Then combined with Auger, you can able to see the gold and carbon here, how the two things are carbon or distributed gold. So same instrument can give a same image, that Auger spectra and Auger mapping. So I'm able to see those type of structures. So in addition to these two techniques that I discussed, both the technique, the Auger electron spectroscopy and X-ray photoelectron spectroscopy, they will give you oxidation state, chemical composition, as well as electron mapping there. So when depth profile analysis is possible, quantification is possible there. But here, this being XPS, in case of hydrogen, helium, you can't detect, because that is not possible. Above helium, you can detect any element in case of XPS, but in case of Auger electron spectroscopy, you can take lithium metal, but lithium solid and any other above element that of lithium, lithium, you can detect all other elements. So the last technique that I'll discuss is secondary ion mass spectroscopy, that is SIMS. The SIMS is widely used, and this is a common technique that can be detected each element from the periodic table, from hydrogen onward. Each element can be detected by using secondary ion mass spectroscopy. So it was first, J.J. Thomson, built mass prototype by M/Z ratio, and then that concept was put into practice by Francis Armstrong, and later on it was different types of SIMS at University of Vienna prototype which was established 1940. Then different detector like time of flight detector introduced, and so far the smart spectroscopy, mass spectrophotometer are now one of the most powerful analytical technique in chemistry that is used. So here the principle lies that here mainly based on the ion beam bombardment, instead of your electron in or X-ray in, here you are bombardment of sample surface. This is the sample surface here. On the sample surface, the matrix atom you can see here, blue one, and then you have a green one is impurity atom, and this primary red atom, primary beam, that ion beam, that is falling on the samples. The bombardment of sample surface with primary beam of intensity IP by smart spectroscopy, then what will happen? You will emit secondary ions. You can see the secondary ions, they are emitting here. Either it will be, impurity atom or the matrix atom, or even that's the incident atoms that can be combined. So mainly the bombardment of sample surface with primary beams, ion beams we are doing, and it is used to create whatever the ion beams, after bombardment, that different secondary ions is coming out. So that ion, so we are detecting by this, secondary ion mass spectroscopy. It is used to characterize the surface and subsurface region of the material based on M by E or M by Z ratio measurement. So, or the ejected particle under ion movement. What are the particles coming out? That M by Z, or is called M by E, that ratio we measure. So it involves the energy transfer from primary beam to the which the energy that the secondary, that ionize the atom, that is the secondary atom, the IES. So characteristic features are mainly, it can be quantitative analysis possible by using this technique. It is a very, very high detection sensitivity of order of 10 to the power 16 to the power 13 atom per centimeter cube, and it's a very dynamic range up to 5 order magnitude and very high resolution depth. High depth resolution is possible up to 20 angstrom, and it can be bilateral resolution is so high that ion microscopy can possible by using the secondary ion mass spectra. You see the components like XPS, you have a primary ion source here, so that for example is primary ion source here, from where the primary beam is coming and falling on the surface. And then, but when you have an ion extracted electrode, that ion extraction is from here to here. There is a plate extraction electron is there. Whatever the secondary ions is generating, that will extract from there and send it to the mass analyzer here. This is the mass analyzer it will send, and then we have an ion detector here and high vacuum ejector is secured here. So once the ions are produced, it go on high potential, it reach to the ion detectors here. So the primary ion source we are use mainly 3 types. One is oxygen, 2 plus oxygen, and cesium and gallium. Oxygen is used for electropositive element like boron, aluminum, etc. And cesium plus is used for electronegativity species like nitrogen, phosphorus, arsenic. Whereas gallium is used for lateral resolutions. So if you see different components here, the ion extraction, that the secondary ion formed at the sample surface are immediately removed. So by this ion extractor or immersion lens, and transfer lens from the real magnitude image, the sample surface, to the spectrophotometer, the spectrometer will take to the detector by the ion extractor. So then you have a mass analyzer. So that will be depend on 3 types mainly. The time of flight, ions with same energy, like 2 ions are generated in 2 ions of same energy, but a different mass of travel with a different velocity. So you can able to identify the drift space, that measure the time taken to travel a drift space. Like it generated from here and detector is here, it will go like this, a hemispherical pathway. So here to here, so both ion 1 and ion 2 that is generated, so that have same energy, but being there different mass, one is heavier than the other. So because of that, they may different mass that they travel with a different velocity. So they from the time scale, that how that they are traveling that mass because of the smartphone. So time of flight, so how much time is taking from there, you can able to differentiate. The simultaneous detection of many elements is possible here, and it is a high transmission resolution and high mass range can be measured here. And the another one is quadruple. So here the certain M by Z each detector for a given ratio of voltage. Like how much voltage you are applying is depending on that certain M by Z will be reached to the detector, or M by Z or M by E. So that from there you can identify the element, the component, or you can have a magnetic sector, a degree of deflection of ions under magnetic field. You can apply a magnetic field and how this ions are generating, so they get deflected degree of deflection depending upon the M by Z. You could say M by Z, M by E, or M by Q, all are same. So M by Z ratio you can able to find out. So it has again have high resolution and transmission, but it has a detection limit is less in this case. So the third one is the ion detector that we use. So ion detector mainly that microchannel, that this is the microchannel here, it will be this zone. So that microchannel, that MCP, that array of miniature electron, various multipliers are there. So it can, an ion passing through the channel hits the inner channel wall and produce secondary electrons. And then that ion detectors, once it's produced, they are secondary electrons which measure, and you could able to identify what is the specific things, materials there. So this needs a high vacuum for this. So the secondary ion that it yields, how much is produced, that depends on the sputtering primary beam yield. So since the material is here, and here you have a different atoms, and you are bombarding with primary ion beam, So primary ion beam, this beam intensity depends on the generation capability of the secondary ions, and ion yields is the fraction of spotted ions to that of become ionized. How much ion that ion yield mainly deals with the fraction of the spotted ions that becomes ionized. That means because of the primary ion, how much secondary ion yields, that it's measured here is dependent upon the element and chemistry of the spotting surface, that how rough is the material, how dense is the material. And oxygen spotted on the surface will increase, as I told, positive ion yield. It will take place in oxygen, because cesium we have a negative ion yield. So you can see here, so all those yellow atoms, they can be used by the oxygen primary beam, or a green one, you can use the cesium primary beams. So most of the element in the periodic table you can able to identify from, you can see hydrogen to bismuth, and then some of the device, and this inner transition element that can be identified. So variability in ionization efficiency lead to different analysis condition as indicated in the periodic table. So depending upon what is the primary source, one able to identify different material. This seems application mainly you can do a mass scan, you can identify different elements present on the material. This is a mass spectrum ZNO sample with lithium, sodium, potassium, chromium. You can see all those elements, and you can also do a depth profiling by through the ion beam, because of this ion, this bombardment. So once the top surface removed, you can go inside, and inside and able to see the dopant diffusion, how different dopant you are different. For example, you're doping cadmium in zinc oxide or something. So what will happen, how the cadmium is distributed, spotted inside. So those things are measured. Isotropic enriched superstructure, like isotopic labeling can be, differentiation can be done. And organic layer structure also you can do in this, and impurity stress level is possible. And ion imaging, that in addition to the spectra or depth analysis, you are able to do, like whatever the ions is producing, you can image that ion, and characterizing content of the sample you can measure. You can identify by ion imaging, and impurity after processing, how much impurity generated, or impurity is there in the material, and different material distribution, and chemical analysis, as well as 3D mapping. You can once you have a different elemental information, you reconstitute the 3D image using software, and you're able to find out what is the material. There are different, different internal features you can able to get. This is an OLED structure that you can see. In the OLED, you have a different layers is there. You have a knife, then TCTA, then this is GBP, then it's ITO. So on the ITO substrate, different layers is there deposited on OLED structure. And then by this ion imaging, you can see that you have a top layer is this, then this, and finally you have a ITO substrate. So these different organic component that is deposited here on the substrate. So that for this analysis, you can use a dual mode like spotted beam. So you can use this SIMS technique and identify, depth profiling. You can identify here. You can see initially you have this layer, you can that pink layer, you can have here you are getting, then it vanishes. But similarly, this if you see ITO, here it is 0, then ITO, here it is increasing. So depending upon the depth, the different layer, you can able to say the depth profiling is possible. And then, as I told, that imaging is possible, ion imaging. You have a primary beam, and then you have a secondary beam that going to the detector, and intensity recorded as a function of primary beam position. You will able to, depending upon the position, how different elements are present in the sample. You can see silicon, and then if the green is carbon, hydrogen, then you have a nickel, metallic nickel is brown color. Then you can see how combining these three, you can able to see the distribution given on the atom surface in a circuit board, electrical circuit board, how the different atoms are distributed. That chemical analysis can be possible. And this is a drug, how this drug is encapsulated inside the material, inside a particular structure, in a nanoparticle or liposome. So those things can be identified. You can see here sodium atom distribution inside that. The sodium deoxycholate on the surface of that material, so you can able to see how the different components in the structural mass analysis. So mainly in that material distribution is possible, and composition analysis can be done by using this ion imaging technique. So this ion imaging technique can also be used for generate a 3D mapping structure. You can see image from the increase different depth, like you take this is the sample substrate, you have a magnesium, gallium, iron, yttrium, how these on the surface, how they are distributed, bulk or cross section if you take, and then once you have this 2D image, a different like a 3D, like you take a cubical portion of the sample surface, and then if you know from the top surface, from the inside, and then from the lateral side cross section if you take, and then you take the image from the increasing depth can be obtained, and hence a three-dimensional data can be generated. So raw data file contain each of the XYZ coordinated different coordinate. You can get that mass spectra, and then this mapping you do, and then you combine this in 3D chemical mapping. You will be able to see how the magnesium is distributed in the layer, how yttrium is distributed in the material. So those type of mapping can be possible. But here you have to take care many things, that analysis condition, that you have to look at the primary beam, that you have to choose a proper primary beam, because that is the intensity or the strength of the primary beam mainly affect that secondary generation, detection limit, resolution. So you have to choose a proper primary beam for the mass spec SIMS analysis, and the beam energy has to be chosen accordingly, so that ion beam mixing, that two different ions, if they somewhere they may be mixed, so you have to identify proper beam energy to differentiate them, and angle of incidence that depends upon the depth profiling, all those things, it depends. And sputtering rate, how much is the sputtering rate, determine the mass, energy, angle of the incident, so that that the energy beam is falling on the surface, that primary ion beam. So there is sputtering rate, the detected area. So how much area you are collecting, that secondary ion generated from the whole surface, what is the area of the cross the detecting, so that is also depth profiling, and species to be monitored, like its detection limit affected the low current rate, high input implant standard dose, and contaminated instrument. If instrument is contaminated, then the species to be monitored, those things are difficult. So energy distribution, secondary ion energy distribution from the sample surface varies with ion species. And you have a insulator effect also. There is a charging may occur because your ion bombardment is there. If there is not proper pathway to remove this ion, so what will happen, that whatever the primary ion you are putting, so that may cause an insulator effect. So the mainly two things that I am discussing here out of so many limitations and constraints. So two principal methods that elemental sensitivity for quantification studies is that, if you see here, the use of ion inflated standard with accurate known fluence. So particular fluence energy of ion primary beam that you have to use here for elemental sensitivity, especially the quantification you are considering, you have to choose particular ion beam energy, and that use of bulk sample top to accurately. So you have to compare with the use of bulk sample top to accurately known known trace element concentration or atom density. So that can be possible by if you have a known standard, it's very good. So then there are various, constant, as I told, that ion beam mixing, then depth resolution is a problem, and segregation somewhere atomically mixed and segregated, so those charge driven diffusion, matrix effect, surface effect, and here is one example I'm giving, that mass interference you can see here, like bismuth, and this is 10, and then you have a monitor bismuth 11 is there. So those type of things can be monitored. But if you have a arsenic 75, and this structure you can see silicon, oxygen. So here also mass is 75. That you have to particular energy you have to see, otherwise what happens, it can be wrongly detected as a arsenic instead of this. So you can see the spectra, log spectra, you can see here the arsenic is like this and silicon is going decreasing here. So if you spectral, if you taken particular electron rejection, that the energy you can able to select and can able to identify the differences between these two elements. And like phosphorus 31 and silicon Si 30 hydrogen 1. So here mass resolution del m by m, you can see though there is a equivalent mass, so high mass resolution you need to identify those structures. So if I compare the surface technique what I discussed today, the three XPS, AES and SIMS. So here in primary beam in XPS is X-rays, whereas this AES or the electrons, where SIMS it is ions. And if you see that electrons is mostly out in case of these two XPS AES, where here it is ion. But in all sample is possible, charging is here, though it takes place, this mainly conductive, where all sample and charging is possible. If you see the depth profile, XPS is go up to some micron range, whereas AES and 10 nanometers, XSIMS is about depth, is analysis area is 100 nanometer depth. And sensitivity almost similar, though it is XSIMS is little bit higher sensitivity. Element, as I told, all element except hydrogen, helium can be here. Here is isolated lithium, is not possible here. Here is all elements can be possible. So identification is very less than ppm, you can able to detect. And quantification is possible, but we need standards. And molecular identification in XPS molecular is not possible, mostly possible. But here oxidation states in XPS AES, oxidation state you can get elemental, chemical, both the informations. And this is non-destructive if you are not sputtering, and if it's always is a destructive technique. And this can be non-destructive if there is no sputtering. That means this XPS and AES both destructive, non-destructive technique. But AE always in ion beam bombardment is there, always it is, it's a destructive technique. So today's class, we mainly discuss three techniques, surface techniques that study the outermost layer of the material that is about less than 100 angstrom. So this electron spectroscopy, I discussed that XPS and Auger electron spectroscopy here, that is mainly used for chemical composition analysis and chemical states. And then also depth profiling is possible, XPS and AS imaging is possible by using this electron spectroscopic techniques. And if you take the ion spectroscopy, that I discussed only one, that is secondary electron ion mass spectroscopy. Here both ion, primary beam ion you are applying and you are getting a secondary beam of ion, and here that is possible for mass scan, depth profile, as well as ion imaging and 3D reconstitution using this ion image. It's possible, so you'll be able to get more of the surface phenomena in these three structures. So by the end of this class, my second module, that is material characterization part, is over. So I will give the assignment in next week. I will send most probably this assignments. So please submit the assignment in due time. And if there is any doubts in this course, you can mail me at my email ID, or you can send it to this HBNI, so they can also transfer me all those questions to me. Okay. Thank you.